Hi, good evening. So, today we will discuss assignment. Here is a 20 question. Okay, so let's wait 2 minutes for maybe some people are joining. Then we will start the questions. Okay, so first question is in a PN junction diode under elimination at short circuit current condition. These are the four options. PN junction diode under elimination at short circuit condition. Okay. Environments. So which option is correct? Let we have P and N, and which is sunlight, let's say eliminated, and which is short circuited My network problem, I think. 1 minute. Okay, so what is the condition? Condition is that which is short circuited. Why, let's say this is wire. So please now answer the question. Yes, please. You can write your answer in chat box. So what will happen? The photocurrent flow from P side to N side in the diode. This is junction. Let me highlight it. This is depletion region or PN junction interface. So, do you know majority and minority charge carrier? We have already discussed in last class. Quasi-Fermi level are. So, what will happen under illumination and short circuit condition? When sunlight is heated or absorbed by the material, charge carriers, minority charge carriers are generated. If minority charge carriers are generated, then minority charge carrier move across the depletion region due to the drift. Okay, answer B is right. Where is the electric field? Due to the drift. You know, electric field direction. This side is positive charge at the depletion region, this side is negative. So this is positive to negative electric field direction, and minority charge carrier if they generate in the PN junction, they move due to this electric field. They feel force to charge it and electric field E. Okay, so let's move for next question. So this is also question how wide the depletion region. These are assumptions. No free carriers in the depletion region. In the region away from the junction and depletion region, minority carrier determine the current. Okay, so minority carrier is the region. Minority carrier move by the diffusion in the region away from the depletion region. But in depletion region, due to the drift, in bulk, electric field is zero. These concept we have already discussed in last class. So let's move for next question. Which of the following is are correct for the direct band gap material in the dark condition? Yes, please. So which of the following is are correct? Yes, please answer. Which of the following is are correct for direct band gap material in dark condition? Do you know direct indirect? If material like that in EK diagram, this is so. Sorry, today's my internet problem. I think. Yeah, connected. 1 minute. Connected. Okay. So this is if delta k is 0, then belongs to direct band gap. But delta k like that k1, k2, and charge carrier wants to move from conduction band to valence band to conduction band. Then delta k does. So this is indirect. Okay. So here is the question. What is the question? Which of the following is are correct for direct band gap material in dark condition? Not eliminated. So let me tell you the answer. First option is space charged region dominated a total current and the additive recombination current can be significant in the dark condition. Space charged region dominated the total current. Where is the space charged current region? Here is the space charged total. These This region is known as depletion region or space charge region. Okay, so here is the total dark current dominated and rotative recombination current can be significant. Other one. So let's move on next question. 1 minute. Let me discuss this. PN junction in dark. Let's give me a minute. So no generation of carrier. Yes. If there is no illumination, so the generation should be. There is no generation. Okay. Value depletion approximation. No generation or recombination in the depletion region. Low level injection in the bulk and bulk electric field is zero and also is the so these are the assumption or ideal condition for the PL junction in dark. Let's move on next question. Which of the following statement is correct for unbiased PN junction diode under elimination? Yes, please. So there is no generation or recombination in the space charge region. Holes move from N side to P side, while electrons move from P to N, and carrier concentration is much above the equilibrium concentration in the both P and N region. The Quasi-Fermi level of the electron and holes are equal, and holes move from P region to N region, while electrons move from N region to P region. Unbiased P-N junction diode under elimination. Let me let's say P and N. This is unbiased and sunlight. This is sunlight. Do you know what is the majority charge carrier from P type and L? Okay, answer is holes move from N to P. So in P, majorities is holes, while this is electron. Let's say some electron may be, some hole may be. So now choose your answer. This is negative immobile charge carrier. This is PN junction. Now let's check these options. Holes move from N region to P region. or also move from P region to N region. Okay, B. And other. So let's check the answer. Hole move from N region to P region, while electron move from N region to, sorry, P region to N region. And carrier concentration is much above the equilibrium in the both P and N. And B is the right option, and also the C. And you can check in picture non-equilibrium condition. This is non-equilibrium condition. PN junction under elimination, and short circuit condition is P0. There is no net recombination is SRA, and concentration you can see is goes up that much. Okay, so carrier concentration is much above the equilibrium concentration in both P and N. Okay, your answer is correct. So let's move for next question. I think this is, which of the following is correct statement for elimination PN junction diode? Yeah, carrier concentration is carrier generation at short circuit current condition is larger than the open circuit condition. There is no generation of the charge carrier at open circuit voltage. Space charge region become wider under the open circuit voltage, and the recombination current in the diode balance the photocurrent at the open circuit voltage. Yeah, one is photocurrent, other is diode current. In solar cell, there is two type current. One is diode current, other is photo generated current, which is shifted to our whole spectra. One minute. So this is due to the fume. This is photo. So recombination current answer is D. Please check your answer. Give me 1 minute. I will be there. Okay. No. Yeah, I will. Yes, please answer. D is the right answer. So, recombination current in the diode balance the photocurrent and at open circuit voltage. Okay, we have PN, we have solar cell, and two type current are there. Let's see. This is resistant. This is series. This is the circuit for the solar cell. So one is photocurrent, other is diode current, and these are opposite in sign. So photocurrent is higher. So this is, let's say, minus. This is plus. The whole is total current is IT is lower the whole spectrum of PN diode. That's why this is shifted to the negative side too much. This is VOC at JSC, closed circuit current. This is VOC, open circuit voltage. Okay, so recombination current at the diode balance the photocurrent. Diode current balance the photocurrent. Next question. Which of the following strategy are used for improving the quantum efficiency of solar cell? Surface passivation, making cell with significant more than the carrier diffusion length, making anti-reflection coating the top of the cell, texturing of the front surface. So which of the following strategy are used to improve the quantum efficiency of solar cell? Okay, so A, C and D. Let's discuss. You can see in picture. Surface passivation obvious. There is loss at surface also in C. Making anti-reflection coating on the, if we making the anti-reflection coating, then our quantum efficiency goes up. Texturing of the front surface like in silicon solar cell. So these are the strategy are generally used to improve the light absorption in the material. Let's say we have material and light is incident, so the light is also the reflected, so this light is useless. If we want to use this light, then we are anti reflecting reflection coating apply on the top surface. Also surface passivation, improve the surface quality. Then we improve the surface quality at the top. There is reduce the loss of incident light. Then light loss is reduced, then more light is inside. If more light is inside, more number of charge carrier are generated, and this leads to improve the quantum efficiency. What is quantum efficiency? Number with respect to the charge carrier are collected at the electrode or generated per second with respect to the incident photons per second. So this is ratio. If the light is more, then charge carrier will be more if the defect is less in the material. Okay. So material quality also dependent. This is low defects. If material has low defects, then quantum efficiencies will be high. And okay, so let's move for next question. Recombination in the bottom layer of the top illumination solar cell can be manifested by a drop in the. So answer is there also, but let's discuss. Drop in quantum efficiency at the longer wavelength. Recombination in the bottom layer of top illuminated solar cell can be manifested by. If we have illuminated that side, this is top, at bottom, what will happen? Drop in quantum efficiency at longer wavelength. Why this is the answer? So let's hear the short wavelength are absorbed at the top and longer wavelength goes in absorbed by the bottom. Okay, so drop in the quantum efficiency at longer wavelength. If recombination in the bottom layer, okay. If question asked like that, recombination at the top, that's the bottom replaced by top, then what will the answer? Quantum efficiency, drop in the quantum efficiency at shorter wavelength. Okay, if material has light is passes through, so shorter wavelength is absorbed by top surface and longer wavelength light is absorbed by bottom surface. Why this is? You know, if this is high, what will happen? This will go, and if this is low, this will be high, inversely proportional to. You know, I equal to I naught to the power minus alpha coefficient like that. So this relation will be used to determine the depth of the penetration of the light. Okay, So this is next question. Which of the following represent the long base approximation for p-n junction diode? Here Ln and Lp are the diffusion length of the electron and holes respectively. Xn and Xp are the end of the equilibrium depletion region in the p-n and p side of the diode respectively. So answer is D. Which of the represent the long base approximation? So long base approximation you can see. Sir, I think already discussed in class. Xn and Xp, Xn and Xp are much less than the diffusion length of p-n and hole respectively. This is approximation, long approximation for p-n junction diode. Sorted base diode, diffusion length should be the higher to the respectively equilibrium ends depletion region length. Okay, so these are the approximation for p-n junction, long and short. Next question. Following parameter doesn't affect the quantum efficiency of photovoltaic device. Yes, please answer this question. Sorry, this place. Yes. Absorption of coefficient, thickness of the device, applied electric bias, surface quality. Does not affect the quantum efficiency. Please choose the right option. Okay, see. Yes, we have already seen these are the effect, but electric applied bias is doesn't affect. Other is if absorption is higher or lower, then quantum efficiency is directly affected. Thickness also and surface quality also affect the quantum efficiency, but electric applied biases doesn't affect the EQE, external quantum efficiency or quantum efficiency. So these are the dependent factor. Surface passivation, low surface recombination, reduce the reflection loss, SRH, increase the cell width to improve the photon absorption, and light trapping to prevent the photon from the escaping. Okay, so let's move for next question. Following is are correct for design and operating or operation in the efficient photovoltaic device. Band gap of the semiconductor. Easy is band gap of the semiconductor. So choose your correct answer. Please first choose your correct answer, then I will discuss. I will show you the right options, then we will discuss. Yes, please. Low movability of charge carrier, minimization of recombination rate through the device, high surface reflection from the cell surface, maximize the absorption of the photon. If energy of the incident photon is higher than the band gap, low surface reflection from the cell surface. Design operation of efficient photovoltaic device. So these are the right options. Okay. Mobility should be higher also. If you want to, we does not want to. Minimization of recombination rate through the device. Obvious. High separate reflection from the cell surface. No. Sorry. Band gap should be incident photon light has much higher as compared to the band gap and low surface reflection from the cell. This should be high mobility. Okay, yeah. Which of the following device characteristics determine the Javi curve illuminated PN junction solar cell photovoltaic device? Let me give you. This is JC open circuit voltage. Okay, so which of the following device parameter are determined the Javi curve? And I want to find out the maximum power, which is, let's say this is Vn J. This is maximum power point. Let's see. So here is the maximum power point is the product of VOC and JC. No, P max equal to Jm into Vm. Okay, maximum extracted power Vm or Im with Vm less than or equal to the VOC and current also is the less than of the SC. This is right or wrong? And at maximum power point, partial derivative of power with respect to voltage will be 0 or not 0. So answer B and D. B is correct. Obviously we can see from the curve and maximum power point partial derivative of the power with respect to voltage should be 0. So the open circuit condition, device is correctly response as. Please answer. Let me put the charts. Let's see. Okay. The open circuit condition. PN junction photovoltaic device is correctly represented at. Answer is Z. This is JSC. Here is VOC. Open circuit condition. What is open circuit condition? Let's say this is device are not connected. So current can't be flow from here to here. So current will be 0 and voltage here is the open circuit condition here. This is the point VOC. Here this line is goes to 0 current, but VOC is the voltage is not 0. Some voltage is, if we measure via voltmeter, then voltage will not be 0. But current at, because resistance is infinite, let's say R is infinite for open circuit. If resistance is too high or infinite, so what will be the current? V by R equal to I. Put infinite, I will be 0. Okay. Yes, please. So this is the right option. Any doubt? Let's move on next question. The photocurrent in a PN junction diode depends on diffusion of the majority charge carrier, applied electric bias, intensity of the illumination, quantum efficiency. Photocurrent in a PN junction diode depend on what are the factor C and D. Okay, so these are the intensity, obvious, we know. If number of photon is high, more photon means more electron hole pair will be generated, more charge carrier are generated. Okay, so means quantum efficiency will be high or photocurrent. If charge carrier is high, then also J is current density or current will be high, and also quantum efficiency will be high. If quantum efficiency is high, then photocurrent is also. These are correlated, directly dependent to each other. Photocurrent is high, means charge carrier is high, means loss is less, means quantum efficiency is high. Okay, so you are right. Your option is correct. Okay, so let's move on next question. The improvement in the fill factor of a particular solar cell device could necessarily lead to. B and D. Okay. Other, please answer the question. Fill factor. Let me discuss with you fill factor. Let's say this is sorry. This is ideal solar cell which has rectangular shape of IV, but in practical some resistance, series and shunt resistance is there due to IV curve look like that. This is real and fill factor ideal solar cell to real ratio of these two define the fill factor. Okay, so P and D is the right option. Improvement in the fill factor, particularly solar cell device, is necessary to decrease in the bias dependent current and increase the maximum power point, etc. If this is the 2 point, this is maximum power point for ideal. So this is high as compared to real. So if power is high, then fill factor also will be high. Maximum power point goes to near to ideal solar cell. If and bias current dependent, decrease in the bias dependent current. Improvement Okay, bias current dependency will be if less, then fill factor is good. So yeah, here is the next question. The expression for current density in eliminated PN junction diode. This is the J net equal to JSC minus J dark. Which of the following is correct between V equal to 0 and V equal to VOC? JC is the source circuit current at zero bias. J dark is a bias dependent current, and J net is total current. VOC is the open circuit voltage of the device. So we have, yeah, which of the following is correct between V equal to 0 and V equal to VOC? Where is the 0? Voltage 0 here, and voltage equal to VOC. So D. Okay. So your option is correct. J net is less than the 0. Also you can see JSC also is less, and J dark current somewhere here. This is J dark goes to down if photocurrent is there. Okay, so your option is correct. Yeah. Next question. For a p-n junction photovoltaic device, as temperature increases, then mainly VOC increases, VOC and JC both increases, VOC and JC both decreases. Temperature. What will happen if temperature is increases? Let's say this is heat due to it or due to the temperature. So VOC is decreases. Why? Okay, please think about this, how they are related. Find the expression or physics behind this. Next question. The current density p-n junction under elimination given on. This is the expression. M is the ideality factor at open circuit condition for the, yeah, at open circuit condition for the Ideal p-n junction above acceptance modify has 2. What will happen at open circuit condition? We have already discussed. Current will be, resistance will be infinite. So, sorry. If we apply on low, 2, then this is 0 if R is infinite. Current is 0 and V will not 0. So JV will be 0. So now please solve this equation. So JVD is also right. Can you find the VOC? If current is 0, then this is point is VOC V equal to. So this is equal to VOC. Please apply here and find out the answer. Can you solve this equation? 1 minute. Let me show you. Current will be 0 and please equate the 0, this expression, and solve this equation. We will get the expression like that. And fidelity factor depends the direct or indirect band gap. Clear? Any doubt? You will get this expression and you know this is also okay. So no doubt we can move for next question. Yes. So yeah, this is the next question. Consider highly doped P and silicon diode with acceptor and donor ion concentration are given 10 to the power 19 per centimeter cube and 10 to the power 18 per centimeter cube respectively. The hole diffusion coefficient in inside is 10 centimeter cube per second and lifetime of holes 10 to the power minus 7 second. When the active area of the device is 10 to the power minus 4 centimeter square, the reverse saturation current in ampere of the diode will be. These are the intrinsic carrier concentration and constant factors. Boltzmann constant and electric charge. These are the options. So let me answer is B. Let's discuss the I naught is the reverse saturation current equal to Q area of the device and diffusion coefficient and concentration of the respective divided by diffusion length. So here is the highly doped P. So hole goes saturation due to the majority charge. Here will be holes. So please see the solution. We can put this value, but we have to also apply and what is P and N, or we can apply what we know the moment. P and concentration of hole and electron, but this is highly doped. So what will happen? Holes and donor we can replace by, so we can calculate the concentration of holes. This is donor. Okay, so here is the another expression. Please apply these two. Let me first find out the Pn. We have intrinsic carrier concentration 10 to the power 10, sorry 11, and donor ions concentration 18. This will give you 4 per centimeter cube. Okay, so this is the step. Now you can also find out the diffusion length with respect to holes. So these are also given. Diffusion coefficient is 10, and also the time, this will be this step. And now you can find out the saturation current. We have all these. Have charge area is also 10 to the power minus 4 centimeter cube. Diffusion coefficient, number of holes in and type, and diffusion length of hole. Okay, so apply these. Please put these value in this equation. I equal to I naught, sorry, the saturation current I naught equal to QA, diffusion coefficient and number of concentration with respect divided by diffusion length. Please see the solution. If you have any doubt, please ask. So please remember this equation. For this equation, we have also diffusion length and one, two, and three. We have these three equations. Then you will get the saturation. Any doubt? This is misprinted here. Any doubt? If don't, then we can move for next question. This is the next question. The PN junction solar cell VOC and JSC are given. A second also VOC and JSC also given for second solar cell. Assuming both are obey the ideal diode equation, okay. What are the value of VOC and JSC when the two solar cells are connected to the parallel? These are connected to the parallel. Let's say first, second, connected like that, and here is the you will get here power by the solar cell power box. So what will happen in parallel? Let's say current are coming in. Total current J1 plus J2 for first and second, and V is the same for both. Okay, so let's see the answer solution. We know the diode equation. J is equal to Z naught e to the power cube VOC by KT minus 1. Here we will use M equal to an identity factor for ideal diode. So change this equation like that for Z naught. For first solar cell we have current is 20 milliampere per centimeter square and VOC equal to 0.5 volt. Put this value here in this equation first, and after solving we will get Z naught equal to 7.66 10 to the power minus 8. Similarly, for second solar cell, okay, now in parallel, so voltage are equal and current will be added up. Okay, so this is the concept for parallel. So current, we know 20 and 16 are given, the total current will be this, while open circuit voltage at open circuit voltage we know the total current will be 0 and V1 equal to V2 equal to VOC. This is the concept for solar cell. Okay, apply this concept here. Put the value of JSC1 and JSC2 or VOC So now you can find the VOC of and will be equal. So here we apply the above concept and equal the VOC V1 equal to V2. After applying, you will get expression for VOC KT by Q ln Js sum of VOC JSC current with respect to the J naught and for first and second plus 1. So KT by Q at room temperature is 0.026 volt. Put the value ln and JSC is 2060 and we have already found out the J01 and for first and second solar cell. Put these value, solve this equation, you will get 0.52 volt. Okay, so this is the parallel condition and also for solar cell condition, we know. Then you will able to solve this question. Okay, any doubt? So let's move for next question. Consider a PN junction diode of area 2 centimeter square under illumination 100 milliwatt per centimeter square gives short circuit current density 25 milliamp per centimeter square and open circuit voltage 1 volt. Generate maximum power 40 milliwatt. The fill factor of the ideal diode will be fill factor. So answer is Z. You can as fill factor FF P maximum power upon VOC into JC. We have already told you ideal area power by the ideal solar cell extract with respect to the real is known as fill factor, or you can write JMVM from JSC. This is VOC. Okay, so use this formula. Maximum power you have 40 milliwatt and what VOC is 1 volt and JSC 25 milliamp per centimeter square. So please calculate the fill factor. So let me tell you P max P, you know the power I into V, but in you can see VOC is right, but JSC include the area. So please find the area per centimeter square, then you will get P maximum is 40 and VOC is 1 open circuit voltage and JSC. What is JSC? I by A. If you want to find the current, JSC into area. So area is 2 and current is 21. Okay, so this is here. You will get 80%. Clear? So let's move. Okay, for next question. In previous, like that previous, we have already seen the how we calculate the fill factor. This is for this question. Consider PN junction diode. Area is 1 under illumination 100 milliwatt per centimeter square. Give the source circuit current 24. VOC is 1.52. Generate maximum 30. The power conversion efficiency. We have calculated the what is the efficiency? How can we calculate? If we P output upon P input. Input we have 100 milliwatt. Output, what is output? Or you can also use another formula. Eta, what is this? VOC JC into fill factor 1P input. You know FF. Power extract from the real one minute. VM JM VOC into JC. This is output power. So we can also find the output power by P out on P in here FF into VOC into JC on P in. Okay, so this is the formula. So fill factor we have already 82. Multiply VOC 1.52, JC is 24. Divide by 100, you will get 29.98% efficiency. Any doubt? So this is around 30%. We will directly calculate. We know the P input and P output. Output is 30, P input is 100. If we want to in percentage, this will be 30%. Direct. Clear? So this is another way. So I think this is the last question of today's session. Thanks for your kind attention. If you have any doubt, you can ask. Okay, thanks for your complimentary. See you next Monday. Thanks to all of you. If you don't have doubts, so let me close the session. Okay.